Hello and welcome back again to another video. So this time we are starting off with further discussions on the second part of electromagnetism. In the last video we talked about the idea of both of the laws of electromagnetic induction, and we also talked about the case of the magnet which was falling through a solenoid and the type of changes that were happening there. So now we're starting with Fleming's right hand rule, which is another tool. So we've already been through Fleming's left hand rule when we were talking about the motor effect, and now we are starting with the right hand rule. So the idea is that, let's say if there is this wire which is between two of these magnets. So how is EM induction going to happen here? So EM induction means electromagnetic induction. So the idea is that if this wire is at rest, so if it's not moved, or if it's moved, for example, in this case, if it were moved left or right, there would be no EMF induced because no field lines are cut. So in terms of the Faraday's law, I would say there is no rate of change of magnetic flux linkage, or I would say that there is no field lines are cut, so no EMF would also be induced. But if, for example, if I move it in any other way, let's say if I move this up or down in such a way that it actually cuts through these field lines, then an EMF would be induced. And if I give this a closed loop, then that would also cause a current to flow. And the idea here is that I can find the direction of this induced current using Fleming's right hand rule. Okay. So for this, let me switch on the camera again. So with this, what you need to remember is that in this rule, the left hand rule and the right hand rule, the fingers stand for the same thing still. So the left hand rule or the right hand rule, the fingers are the same. So with this as my right hand rule, the thumb is still force or motion, the first finger is still field, and the second finger is still current. But things have now changed dramatically, because when do you use the left hand rule is when you know the field, when you know the current, and you have to find the direction of the force, right? That's for the left hand rule. Again, let me do this. So you know field, you know current, and you want to find the direction of the thumb, which is the force. You use this in an entirely different scenario. This time you still know the field, but you also know the direction of the thumb, which is how this conductor is moved, and that's when you find the direction of the current. So for example, if I use it in this context, again I start with the same ideas. So my first finger, the field is what I start with, that must point like this. My thumb points up, so my second finger then points inwards. So in this case, the induced current is going to flow in a direction like this. Right, so that's how you use Fleming's right hand rule. Now let's see it in action when we talk about the AC generator. So with the AC generator, the diagram at first looks pretty similar to a DC motor, because you still have those magnets and you still have a coil of wire which is placed in between. But something that you would note is, first of all, this thing is also different. There we had a split ring commutator, here we have slip rings. And carbon brushes is still here. And also here we previously had a power source, but now we have a bulb, because things are different this time around. If I think about the DC motor, then in terms of energy, I would say that it converts electrical energy to kinetic energy. Here it's actually the reverse. Here it would be converting kinetic energy to electrical energy, because I would be rotating the motor on my own. And this is what is used in a lot of power generation sources. So for example, like with hydroelectric power, the water hits the turbine, it makes the turbine spin inside the generator. That's what produces electricity, right? So this is different. Okay, so as the coil is rotated, field lines are cut, leading to an induced current flowing in the coil, the direction of which can be found using this rule that we just talked about, which is Fleming's right hand rule, right? When the coil is horizontal, you can obviously see that the field lines would be like this. So the greatest number of field lines would be cut. So when this is how the field is going, as it starts to rotate, it would cut through the greatest number of field lines, and that would lead to the maximum EMF as well. And similarly, when the coil becomes vertical, so right at this instant, it's moving parallel to the field lines. It's not cutting through any of those. So in this case, there is no EMF induced since no field lines are cut. So why is this called an AC generator? You can now probably see, because you've talked about AC current, and you can see here that the EMF and hence the current which is flowing is not the same throughout. Some places it's going to be max, other places it's going to be zero. More precisely, it's max when the coil is horizontal, it's zero when the coil is vertical, and at any position in between it would have an intermediate value. What's the idea of slip rings and carbon brushes? So in this case, again, the slip rings are also not rotating. As the coil rotates, these contacts would change with the slip ring, and so would these as it keeps rotating. So all the slip ring does in this case is that it ensures that the electricity, the current which is produced in the coil, can be transmitted to the bulb without the wires twisting. Because if I just had wires, and as this keeps on turning, the wires would twist. So that's the idea in this case. So as the coil goes past the vertical, the direction of the current in each side reverses. Again, let's see how that would happen. So let's say if the coil is in this orientation as shown here, and let's say if this is how it's rotated, so I know that the force on this side is upwards like this, and downwards on this side like this. So let's use Fleming's right hand rule to figure out the direction of current in each of these sides. So in AB, I can see that thumb is upwards, the field is like this, so the current flows inwards. So this is how the current flows here. And then obviously if I do it the other way, so this time the thumb is downwards, so the current is also outwards like this. So the current goes like this, and then obviously connecting the dots, it must flow like this. So that's the idea of the right hand rule. But now when the coil actually flips, when it goes past the vertical and it changes its orientation, then AB would be here, right? And if it's still turning in the same direction, then you can see that previously the current was going from A to B, but when it's here, then the current would be going from B to A. So the direction of the current in the coil is reversing in every half rotation. As soon as it goes past the vertical, the direction of the current reverses here. So that's an important idea. Again, you also have these different graphs which can be made depending on where the coil is starting from. So if it has a vertical starting position, we know that at the start, no EMF would be induced because it's moving parallel to the field line. So no field lines are cut, no EMF is induced. Then it goes in one way. So again, when it becomes horizontal, as shown here, it would be cutting through the greatest number of field lines, leading to a maximum EMF like this. And then again, it would become zero as the coil becomes vertical again. But now if you compare both of these, it's flipped, because previously we had AB here, now AB is at the bottom. Previously we had CD here, now CD is here, right? So it's completely flipped. It was like this, and now it's like this. It's the other way around. But again, it's vertical, so no EMF is induced. Then it goes in the opposite direction. So if I'm calling one of these positive, then this one I would call as negative. That's very obvious. So that's going to be like this. And then the third one, again, it becomes vertical. That's like this. So in one rotation, it's come back to its original position, which is A here, B here, A here, B here, and C here, and D here. So that's what we can see. So then the idea is that the graph here becomes something like this. And that's the graph that we have. After this, as the coil keeps rotating, the same shape is going to keep repeating. For those of you who study add math, might recognize this as the sine curve. What if it starts from a horizontal starting position? Now what would be different? So if it starts from a horizontal starting position, then at first it would lead to a maximum EMF. But then it would become vertical again. So at vertical, you would again have zero EMF. And then similarly, if it's starting from some horizontal starting position, and then if it flips, so the other EMF I would call as negative because the current is flowing in the opposite direction. And then again it becomes zero, and then maximum again because it's rotated through an entire revolution and it's come back to its original position. So in this case, the graph looks like this. Let's hope I can make it well. So like this, right? So that was a sine graph. Again, for people who study add math might recognize this as a cos graph, right? So both of these could be possible graphs. Sometimes this is asked in MCQ, so I'm just letting you guys know that both of these are possibilities. Factors affecting the EMF. Now, this is also something that the examiner asks really often. So, factors affecting the EMF. First one, and it's very easy because you've seen in the last couple of videos what actually affects the induced EMF when we talk about the uh, ideas of EM induction, right? So we saw this in the very first video. So for example, the strength of the magnets is one of these. So strength of magnetic field. Right? Similarly, the affected, so the induced EMF. So strength of the magnetic field, again, the iron core in the coil, or for that matter, the number of turns. So you can see that all of these would basically cause more field lines to be cut per unit time, because if I, for example, increase the magnetic field strength, so your field lines would be more concentrated. Or for example, if I have an iron core in the coil, it's the same idea. So it would increase the magnetic field strength. If you have more turns, so with more turns, again, as the coil rotates, more of the coil cuts through the field lines. All of those go into increasing the rate of change of magnetic flux linkage, or you can say more field lines are cut per unit time, and this is going to increase the magnitude of the induced EMF. So if this is how the EMF was initially, so after making these changes, the magnitude is going to be greater. So probably something like this is what you will see. And then the other way, like this. So this is an increased magnitude. One of these factors I've kept separate on purpose because this is the only factor that affects both the magnitude and the frequency of the induced EMF, and that is the speed of rotation of the coil. So some of you might be thinking why I did not talk about this there. So that's because this is the only one which affects both of these. Now let's say if I have this coil and if I start spinning this faster and faster and faster. Now what would happen is obviously the field lines would be cut faster. That would lead to an increase in the induced EMF and hence the current. But also if you think about it, if I'm spinning this faster and faster, then that one cycle that's also happening faster, so it's taking less time. So not only does the amplitude increase, but it also shrinks. Or in the language of waves, I would say that the frequency of the induced EMF also increases. So in that case, the graph would probably look something like this. And like this. So you can see that, for example, in the red graph, the time for what was previously the time for half cycle now has one full wave being formed in that, right? So that's the idea here. Now this is an important factor. The examiner often asks this in MCQs. So for example, like if for example, if I'm spinning a coil in between fields, so it would say that, for example, if I start increasing the speed of rotation, how would the graph change? So not only would it get taller, but it would also keep shrinking like this, right? So like this, and then it also keeps getting closer together. Yeah, so probably something like this. So that's it for this video. In the next one, we'll be talking about the idea of transformers. So see you there.